some of these wows. And of course, the biosphere is filled with wows, as you well know. And I apologize right from the beginning because many times I could be saying things certainly that you already know or are familiar with, but hopefully you still find it useful to spend this time together. Okay, I certainly miss Krakow and I miss so many of you and my friends there. And hopefully we'll get to see each other in person sometime in the near future. Let's see. This will certainly wake you up. This is a picture taken by Anup Shah, and this is quite a photo. I always like to sometimes see this picture because this mountain gorilla is a wow just by their existence. And here you can see it. Looks like it's having a pretty relaxing, special time surrounded by butterflies. And to me, this is a small little wow in the biosphere, but it's one that makes us certainly connect to our close relatives, primates, and in this case, this magnificent creature and all of the enjoyment that it's getting out of the surroundings with all those butterflies. So it's a good field picture and a good way, I think, to begin. And certainly a lot better than if you had a picture of me with butterflies around me. um, so here you go, selected global ecology wows from biosphere history. And the about, but it's good to touch base. These images reflect the world that we're entering here through this presentation. And here we see examples of various life forms, really, from bats in the lower left corner to fish to wolves, and across the board to these shrooms, the fungi. And here you see a snowy owl. I don't know how often you have snowy owls in Poland, but we have them quite often, the beautiful white or light colored owls that come in the wintertime. And then on the upper right here, you see lichens, which was originally my world. I studied lichens for a number of years. Bees. I mean, this is diversity, diversity of life on the planet. And I think it's very cool, even though many of you again are aware of this. But it's very cool to think of this as Maggie's Sponge Cafe. Um, and of course, the S, the P, the O, the N, C, H, and the cafe, meaning the calcium and the iron. These 8 elements, and 9 if you include Maggie. And you can imagine what the Maggie must be on the periodic table. It's really about as essential an element as you could possibly imagine, right? Because it's so essential in photosynthesis, which really drives the planet or drives the life on the planet in the biosphere. 9 elements, look at that. That, to me, that is a wow by itself, right? And I think we should always make sure our students are aware of this and right in front of us as they're learning, because that is sort of an important story. 9 elements make up 97 to 99% of each living organism in the biosphere. And that's a wide variety of life. And it shows a real unity. Who would ever have imagined that only 9 elements, just moving them around in different ways, results in all these different creatures, life forms, so on. Yeah, that's what I say. and while they're all part of the essential bio and geocycles, just like our own bodies, too much of any of these elements freely available in the biosphere disrupt the established working systems and can even be toxic if there's too many in a given area, as you well know. Our grand home, the biosphere, appears to run most effectively when there are bioconstructs, okay, life constructions, that life is somehow building, distributing, sort of overseeing the development of the biosphere itself. The bioconstructs, sometimes we separate geology and biology, and I think we know that that can be a real mistake. The two really go together in so many ways. For example, a reef ultimately becomes a geological construct, but it really was built substantially by biology, by life. And platforms, the same with platforms, which are similar to reefs, but are just, elongated structures, frequently in ocean environments, but can be anywhere at any time. And they serve to both sequester meaning to store or keep in, and distribute these key elements, these sponge cafe. If we look at the biosphere history and the millions of years of its, quote, wisdom, this is an important story. It's the movement of these elements over time. And that's kind of and that alone is a wow, but then it connects to our other stories here very nicely. So reefs and sediment platforms as cornerstones of the biosphere's global ecology. Reefs and sediment platforms as cornerstones meaning central stories in the biosphere's global ecology, for wanting to understand the planet and how it works over all these millions and tens of millions of years. A lot of it is, again, this creation of storage areas, if you will, such that nutrients can move effectively around the planet and make us all who we are, as in all those pictures we saw. So the profound nutrient flow impacts our biogenicity. Biogenicity meaning, again, I don't even think it's a word. Maybe it's a word that I just invented. I don't know. But our nutrient flow impacts the biological origin of so many geological and nutrient storage areas that we see. We might see a Permian age limestone mountaintop or mountain area, and much of that is of a biological origin, so we say it's biogenic. Excuse me. And here's a picture I think you've seen before. Maybe you've seen it when I've shown it in Krakow different times, or you just know of it. It really goes back to the 80s, but if we could definitely get a picture of this at this time as well. And this is the dark ocean taken from space. And this looks like a cloud above the water, but it's not. It's near the surface of the water, and it's not a cloud either. It's a massive, going for really hundreds of square kilometers of one organism. Okay, and it's off the coast of Scotland. This is a fairly famous picture, and many others are like it. It isn't as if it's one moment of time. At different seasons of the year, this is a fairly common picture in the North Atlantic. And this is Emiliania, believed to be the most common eukaryote. I mean, is anything really the most or the best? No, but is it up there among the most, I'll say it that way, among the most common life forms on the planet, Emiliania, which is a alga, and it's named after its founder. And what's incredible is that when research has been done to look at this bloom, this massive growth of algae, whether we take a sample from here or whatever part we take samples from on a ship and analyze it, it's all one organism. It's not a collection of algae. It's totally dominated by this algae and by the species Huxleya, named after Thomas Huxley, Darwin's brilliant associate back in the 19th century. And yeah, so there it is off of the Hebrides in Scotland. And that's quite a story. That is Emiliania, beautiful organism. an embraceable organism. It's just wonderful. And you can see all the tests or shells in the general term, but tests what we would call with algal growth. This is calcium carbonate. And of course, this is microscopic, super microscopic. We're dealing with the microcosmos almost all the time when we're talking about how the earth runs, aren't we? Microbes dominated it. Really 7 Earths of Earth time, and even do today, because as we know, we're pretty much a collection of microbes within us, right? We are ourselves a walking ecosystem, as we know now through the studies and findings of the microbiome. So it's an elegant shelled, or test as we call it, microscopic alga, and significant global impacts on the carbon, calcium, on the sponge cafe, right? Carbon, calcium, sulfur, sediment and terrestrial surface geology, the real impact on food webs, on biodiversity, on albedo enhancement, and that's through, as many of you know, cloud formation. Clouds can't form unless moisture is condensing on particles in the atmosphere, or else you really can't have clouds. You can't really have the systems we think of. And I put alaga in there. No, that's not a new word. That's a misprint. It should be ALGA, right? Algal. It should be algal, not alagal. Anyways, via algae, like the coccoliths, when they use this particular sulfide or sulfur connected compounds for their own development, and then the gas is released from various algae, such as coccoliths. And that gas becomes particulate matter for moisture to condense on and form clouds. This was something that was realized back over 30 years ago through James Lovelock and others. But the point is that it's pretty amazing that algae not only have all the contributions that we just said through nutrient flow, but even sometimes have influences on building clouds. And this is a picture that shows, again, the depth and breadth of coccolith formations. Here we see from the one extension of the arrow to the other that the geological strata in much of Northwest or much of Europe, really, and certainly extending into United Kingdom and out into the sea bottoms, the sediment area out here in the North Atlantic. This is an old picture, and look at this. It says Atlantic Telegraph. This is just prior to the invention of telephones per se. There was the need to build a line, as you know, across all the way to Newfoundland, and therefore communication systems could evolve or to be developed by humans. And in doing so, that's where a lot of the coccoliths and their dominance was discovered. And it was also discovered that the sediment here at the bottom of the sea and throughout much of Europe is mainly, not solely, but mainly substantially, is a better word, substantially, coccoliths. Coccolithophore is the organism. The coccolith is the material, the shelled or test material of calcium carbonate that's deposited when they die. And as they die and go through their cycle, they fall to the bottom of the sea. We'll see that shortly. But you can see this is really thousands of square miles of the current Europe. If we drill down someplace in Europe, almost any place, but scattered places, not every place, we would be eventually drilling through very thick coccolith deposits from times when Europe was underwater, such as Poland, went through many times of being underwater and being in a different part of the planet through plate tectonics, of course. So here's also a companion to it, so to speak, another common microbe that's not an alga, in his different view of it with its spines that capture food and bring it in. These are protoctists. Like algae, they're protoctists or protists, but they, in this case, are mainly heterotrophic, and they have very different characteristics of other algae. So, and we have them as foraminifera, that again should be an N between the F. I think I was falling asleep when I finished that. I left out my I. Foraminifera. Anyways, here is foraminifera as well, expressed, as many of you know, as pyramids. Almost all the material in pyramids we found is to be from foraminiferan shells. So this is a mini wow, right? I mean, this is something. You think about it, that the amount of material it was able to be. And this is some of the foraminifera. You can look into how they have also chambered areas, and those chambered areas get invaded, if you will, or accepted. It's a better word in this case, by the host foram. And so you have a symbiosis evolve here where the host foram can actually receive carbon from these various, in this case, green algae, chlorophytic algae that have becomes part of this particular, in this case, a Pacific's, I think it's a South Pacific foram. They are also part of all these forams, and all the really hundreds of species of forams are influential in being part of the sediment that becomes important in element distribution and compound distribution, nutrient flow. And when we think of the coccoliths, again, we see just simple pictures showing the lightish color being the deposits of the coccoliths building up in the sea bottom, say of the North Atlantic, with the ocean above. Over time, we have orogeny, right? The lifting up of land masses above the water level, or in some cases, depending upon glaciation into glacial periods, the rise of water, such as the start of interglacial periods, that then and that then can make the changes in where the land areas are. And here during glacial periods, of course, there's less water, and so you also have more land exposed. But frankly, most of the time, as you know, this is occurring a lot through orogeny, the lifting of the land masses, much of the time through volcanic action, plates meeting, and so on. But here you can see, this is meant to show the coccoliths, and you can see cracks in the limestone. And this, of course, hundreds of millions of tons of coccolith shells, mixed with some forams and other organisms as well, but mainly that. And of course, you see forests up above and whatever other kinds of life. And over time, you have what we call differential dissolution. That is the limestone itself begins to have pockets of water because it's very soluble. And so you have different areas that are more soluble than others. You get this kind of cracks in the beginning of caves. You get the beginning then of areas where there's been solutions of the limestone, calcium carbonate, and over time you get hills, right? And high areas mixed with valleys and rivers running through it, etc. Caves beginning to form. This is a profound story. It is one based upon life forms and one based upon these algae, albeit some other organisms as well. And here's a picture reflecting that last picture. This is in China, in a place called Guilin, and it's one of the more beautiful, spectacular areas. All of this is sea bottom. It's no longer sea bottom, and much of this is limestone organisms building these that are remaining from the deposits and now eroded and expressed in different ways as mountains. And of course, they're important nutrient flow and nutrient supply for all of the life around it. This isn't just a mountain story and obviously a pretty picture story, but it's really a source of nutrients for all the runoff and flow to the surrounding areas. Excuse me. So this is just one of really hundreds of pictures. You could take pictures of buildings, right? And certainly in Krakow, talk about a limestone place. Southern Poland, Małopolska is really a key story connecting to everything that we're saying here. Albeit in your world, you have so many, you have various limestone deposits that aren't necessarily coccoliths, that aren't necessarily coral reefs, but are sponge reefs, for example, as we fortunately saw in a wonderful tour given by some of your colleagues there on previous trips, visiting calcium carbonate deposits dating back over 60 million years near Krakow. And so coccoliths have this kind of an expression. They really are important to the earth. They have this connection. One is so microscopic, the other is so macroscopic, both very beautiful, both a wow in and of themselves, I suppose. The remains of calciferous microbial algae, which arose through secondary symbiosis, which we'll touch upon later, dominate vast regions of the biosphere's ocean sediments and land masses. Yeah. So let's look at another example of this nutrient flow through biological means. And we think of Florida, Florida in the southeast part of the United States. And this has been 500 million years ago as part of Africa, south of the equator. And of course, if we told many Floridans that, they might not believe what you're talking about. But we know that that landmass is there, that we have 500 million year old deep rock formations surrounding and around Florida today, albeit extremely deep. Most of it is calcium carbonate above. Originally part of Africa and at the equator 500 million years ago, what we know is Florida and the seas around it evolved as an important storage of calcium and carbon, of sponge cafe, if you will, and remains such today. And we see at 50 million years ago, Florida here is, you can't see it as a landmass, certainly during the usually 100,000 year or so, 120,000 year glacial period, you have much more of the land of the ocean itself being exposed and so on. But here you see Florida only visible as sediment, really. And that sediment forms what we call a carbonate platform, where again, carbon, calcium becomes sequestered here and slowly released. If all of this is released in short periods of time on the planet through the biosphere history, we would not have a planet the way it is now. It would be toxic, just like our own bodies. We can't have an excess. We have to have calcium, but it can't be an excess, uncontrolled flow. It has to be sequestered, and it's done without thinking. The calcium control in our body has very little to do with what we're thinking about. The quote intelligence is more what we've defined, whereas the intelligence of the planet is on a greater level, of course, and on one that is expressed through feedback systems and so on over time, as well as natural selection. And here is the reason for that. It's not coccolith. That is the reason for this massive carbonate deposit on the southeast area of the United States. Florida is one big limestone platform that will soon be underwater. We know that. Soon meaning in this century, a good part of it. Already, a good part of it is underwater in the sense that there's so much water coming in through the sides from the Atlantic and the Gulf and going underneath, amongst the very soluble limestone and flooding at different times, causing these beautiful wetlands but at times that will get higher and higher, as we know through human-caused climate change. This is Thalassia. Thalassia is turtle grass, we call it. It's a beautiful grass, but it extends really for hundreds and hundreds of square miles around in the Gulf of Mexico, near and around Florida. And it becomes encrusted over time, as you see here, and it becomes encrusted regularly each year. This is all calcium building up on these very photosynthetic algae. And in a sense, these two organisms have a little dance going on over time, and that the calcium is from the organism, as we're going to see a picture, is from an alga, a red alga, that is calciferous and calciumphilic. It needs and requires a lot of calcium in its own development and in its own protection. And we see it here, for example, or a species of it, Melobacia. It's a coralline rhodophyte, and it covers the grasses. The grasses do not die from it. Quite the contrary, they do quite well, and vice versa. The Melobacia do quite well on the surface. So it's kind of it's an ecological partnership, one of a zillion of them, right? It's not a symbiosis per se, but it's just as powerful in a sense. And it's gone on for what appears to be thousands of years, this relationship. And it builds these platform deposits. You can see in this aerial view, some of these are coral reefs, but most of this is the calcium deposit, and it extends further around the tip of Florida here. This is just a view that one could see of a portion of it. And it's all of the calcium accumulating and getting to be up to 3,000 feet or 1,000 meters thick, deep. So, because it's going back millions of years, not just thousands of years. And so this is a depository. Here you can see just a cutaway at the surface. Looks like somebody's house or something. I don't know. Anywhere somebody lives in Florida. But here is the calcium carbonate buildup, not from coccoliths per se. There's influence obviously from other calcium carbonate building organisms, but substantially from what we say, which is this Melobacia. Who would have thunk it that a red alga would have this particular kind of influence? But there it is. We have consistent evidence of that. So this wow you're familiar with. No, this is not a piece of meat on the right side on a dinner table. That is a Caribbean island, and that is reefs taken from space. And so calcium carbonate, again, is a big source of reefs, and it's algal driven, as you know. It's algal driven in the sense that the reef is the outcome of a symbiosis between a Symbiodinium, the genus, and various species of that, and its host coral animal. And the reef builds its house, so to speak, where the larvae can often land and grow and form in new polyps and new coral reefs. But it certainly becomes a biosphere heaven in the sense that it supports, or a biodiversity heaven really, in that it supports so much life that are so essential to the biosphere. And of course now is under extreme, well, here you see the masses of the dinoflagellates here expressed as Symbiodinium in these masses forming within the small polyps in this case. And they will photosynthesize, and they actually transfer substantial amounts of carbon to the animal. So the animal, the invertebrate, becomes not only versatile in acquiring food, predator, prey creatures to digest through also just absorption through its body, but it can also become photosynthetic. So this animal becomes photosynthetic, and it can only build a reef once it has the algae. It cannot build a reef otherwise. So this is an amazing partnership, and as you know, under massive threat now, due to and for a number of reasons, but this substantial reason being, of course, the high temperatures in the seas, reaching somewhat ridiculous temperatures. We've been to Tobago off the Venezuelan coast, and temperatures there of the ocean temperatures are 5 to 10 degrees Fahrenheit higher than normal, higher than what's ever been seen earlier, measured in the century and past century. So we have really extremes of water temperature, which Symbiodinium, the alga, cannot survive in. There may be some species, but that can show tolerance of heat, but it's not something we depend upon for regeneration of corals, because it does take time for that kind of assimilation to occur. So this is a major issue that many people are working on. But in the end, it'll have to be somewhat of a nature supported by people issue rather than a techno people issue by itself. We see that a lot of technological directions don't necessarily take us to the answer unless we're somehow really partnering with nature. And here is just some of the expressions of, I didn't take this picture, of coral reefs. This is on the top of a I think 2,500 meter mountain in China, or 3,000 meter in China. This is in Carlsbad Caverns in New Mexico, which has massive caves, and you're essentially walking through a coral reef that's no longer underwater. It's in part of a mountainous zone in this spectacular area, about a mile deep. Excuse me. So yeah, corals we know are calcium carbonate deposits. Here's another deposit that's quite different, another kind of wow. It's not an ocean one, obviously, but it is, in a sense, a platform of distribution of elements, key elements in the biosphere. It even has a human here. It looks like it's my wife or a lookalike. This is in the Amazon in Tipitini, which is in the Yasuni area, a vast area under threat also from oil extraction, as so much of the world is. And this is a massive fig tree, but it's important to note that much of this, if we were able to analyze the cells in here, and these are kind of buttress roots, this is a buttress root. This is all root cells, not all, but mostly root cells, all of this massive tree. The trunk is trunk cells, or the cells that are parts of the other parts of the tree, don't really get going until they're up at the top where this arrow is. And this is a massive tree extending really over 30 meters, 35 meters in the Amazon. Most of these do not last up a long time, but this one's been clearly in the 75-year or more category. And you can see right here that how high the roots go. And it's again because in the Amazon, most of the nutrients flow at the surface from one organism and life form to another. It isn't at all like we have here in our regions. We have more temperate zone in southern Poland and here in Boston area. That is, the nutrients flow deep down. We have deep soil. Here they're being washed away. The soil is very old. It's moved across the equator and back a few times, but it's pretty much stayed near the equator. So it's drained a lot of its nutrients through its rainfall, consistent over tens of thousands of years. So it tends to have most of its nutrient flow at the surface area, almost directly from one dying plant to another, almost directly. And so so natural selection has favored those trees that do not have deep roots in the soil. They would be useless in terms of nutrient supply and in terms of holding its place in the soil. So buttress roots of large fig in the Yasuni Tipitini region of Northwest Amazon These roots do not reach deep in the soils because most nutrients are very near or at the surface and are brought into the root cells via two groups of fungi. As we all know, leaf decomposes, breaking down the leaves, but a different set of fungi that are mycorrhizal, that are obviously involved with particularly phosphorus transfer of the sponge cafe, the P, but in many cases nitrogen transfer and other nutrients, other elements through compounds. So this is crucial, and of course the mycorrhizae are receiving carbon in most cases from the partner tree or partner plant. So yeah, and here we see units of surface. These are pictures that I've taken in trips to the Amazon and so on. And this one is not. This is from another source, and showing in this case the arbuscular mycorrhizae within or somewhat within the root cells. Let's look at another example, but it's not really another example. It's the same example, but another story related to that example. Who would have thought that this picture and all of the Amazon, much of the Amazon, is connected to this country and to this place, this one little place in this country? Chad is a major country in Africa. It's what is it? About 4 times the size of Poland. We tend sometimes to think of countries and places other than where we live as small places. I mean, it just, what is it? We're not familiar with it geographically, geologically, scientifically as much as we perhaps should. But Chad is it's a major landmass in Africa, and it's, again, one also has a low carbon footprint, which is important to note. It's a so-called poorer country in terms of wealth and capitalism, but not in all the other categories that are worth talking about. Community building, helping each other out, not exploiting and making toxified environments. There is oil extraction there, but it's from foreign companies. Usually the people who live there are not too much involved with that. But for the most part, Chad is a low carbon footprint country on the planet, and it's one that's very important to the Amazon. Okay, as many of you know this story, but it's worth reviewing. These are some of the folks that live there. There are all kinds of groups of people there. Most of these people are not really related. They're all different indigenous groups. And yes, yesterday we're here in the U.S. anyway, it was Indigenous Peoples Day, substituting for Columbus inappropriately. So these are people just doing their thing in their communities. The southern parts of Chad tend to be more water, more of a water source area, whereas the northern areas are more desert as they get in part of the Sahara. So Lake Chad is one of the main Chads, and it's said that's a double word. Chad means large lake in the language, one of the common languages of Chad, and it's an ancient lake there, and it goes through wetting and drying cycles. This is a part of the lake itself. This is it over time. The picture on the left was taken in 1972. The one on the right, 1987. You can see it drying out here. This is a massive lake. If you think of the Great Lakes in the United States or other major lakes all over the world, this was many times that. It was a good percentage of the huge country of Chad. And that mega lake Chad includes an area called Bodele. And Bodele is a depression area formed by a wind tunnel that we'll see in a second. Again, Lake Chad, again, you have drying out through long periods over thousands of years, and sometimes hundreds of years. You have a quick drying out depending upon climate. And now with climate change threat, it's even a faster change. And we see the lake becoming more dried, drying of the lake and other ephemeral vernal water areas expands the most diatom concentrated mineral dust Baudelaire region. What we're saying here is that as you get drying out, the lake dries out. What was living in the lake? Algae, and diatom algae in particular. So you have minerals from those algae and other organisms, but not that great a biodiversity in the water itself, except algal diversity. And much of it are different species of diatoms, silica dioxide-based algae, but containing, of course, the sponge cafe, photosynthetic, requiring magnesium, requiring the other elements as well. And they go to the bottom of the lake and become part of the dry sediment as the water dries up. Okay, and then you have, when you look at Chad and Libya to the north, you have a very common high pressure system, whereas air moves around the high pressure like this. Okay, that's a counterclockwise direction, or clockwise direction. Yeah, and clockwise direction goes like that around and brings winds from the northeast down into Chad area, and it brings it to a very specific area. The high becomes very stable there, stays for long periods of time. And then it brings in what's called the Hamatan winds from the northeast to the southwest into Chad, contributing to the low-level jet, this race of air. It's picking up all the sediment, the dust, mineral dust, if you will, that passes regularly through two mountain zones and causes sediment deflation, the loss of sediment, right? The loss of all that sediment. Where does it go? In the air, by the wind. And that's a big story on the planet that we don't necessarily pay much attention to, but now we do. Here you can see it in the picture. You see the Tibesti mountain zone on the part, and the Anidi mountain zone here. You have a natural wind tunnel. The high pressure system is to the upper right here. You can't see it on the picture, but the winds are coming down in this direction, like this, clockwise direction, and picking up the material, especially the dried out Chad area where you see the word dust. You see the words Baudelaire depression. This is all the dried out material, which is algal. It's diatoms, shells, the tests of it, and other dried out portions of it that then are lifted up into the air and carried westward on various currents. And it's done throughout the year, sometimes more than others. Here's a close-up of it here. And again, Lake Chad once extended into this whole area where the arrow is spinning here, that my cursor is spinning. Okay, so it's dried up considerably, albeit it goes through periods where it can be very wet. Right now, who knows, with climate change, it's hard to predict what will happen and how the cycle here will be altered. Why is that cycle important? Because much of the dust content, as well as because of not only becomes mineral dust that's important, but they become vehicles. The diatoms themselves can hold other dust materials, such as from the volcanic mountain zones. So they carry iron, masses of iron is embedded within those diatom dusts, because they become, how can I come, say, micro platforms, as you will. Scientists reported being actually housing other material from the dust material from the volcanic flow, or from once volcanic flow. They're now dormant volcanoes, but they have a lot of material blowing off of them. And so these are the diatoms. You're familiar with them, all different kinds, all different types. The one in the lower right and the one in the upper right are common types that you find in the Baudelaire region. Here's some of the diatomaceous sediment that can get pretty deep. This is just at the surface. This extends down for really up to a mile in some tests that have been done. Very hard to do research there and do tests, but from the studies that have been done, it's pretty deep. It can extend down to a mile of this collection over hundreds and indeed thousands and thousands of years. This is all algal sediment, mostly diatomaceous. It does have also some volcanic remnant material in there as well. As we're saying, that's uplifted as well via the diatom shells. So winds from a narrow parad, with the risk of being repetitive here, sorry, but just to be clear, winds from a narrow passage between two dormant volcanoes carry 25 to 40 million tons each year of mineral dust, mostly diatomaceous. Tests from the Bodali region of the Sahara in Chad and El Jouaf in Sahara, Mauritania, mainly in the Sahara, which is to the west of Chad, to the Amazon, and additional millions of those mineral dust particles to portions of the Atlantic Ocean as well. And here we see some studies over time that have showed a former land surface that within just a few years has dropped a meter over a long period of time. And this will only be replenished when there's wet periods that can then go through a dry period, depositing more algal shells, right? Tests. So you need the cycle. Otherwise, all of these diatom shells and all this sponge cafe will eventually run in slow quantities and not be the conduit for a lot of flow to other lands, such as South America, as we see in this picture here. To be clear, it's flowing from here to here, that a lot of the nutrients that make the Amazon are not only from one organism to another, but they're also being replenished constantly by a flow of key nutrients from the Amazon, from North Africa. And not just from Bodele, they're finding from other regions as well, Mauritania and other regions. And there's the close-up picture again showing the sediment flow. And this is the Tipitini River, nice dark river. This is a healthy river. It's filled with nutrients, filled with more fish than we can count, and indeed than have even been named. This is probably the most biodiverse area on Earth, or among the most terrestrial area, is the Yasuni Tipitini region of eastern Ecuador, northwest Amazon. So that's the flow. And wow. And there you go. You can actually see it from space. You see this light brown material here around this storm of air. It's a comma-shaped low pressure system. It's that right now, much like a hurricane, is moving to the west. And this flow will occur without this particular storm. But with this storm area, you see it more pronounced and more consolidated, shown in one area. And this is moving from east to west, as of course many storms do, especially hurricanes and low pressure systems will do. And this moves and brings this material to the west, where it's eventually deposited prior to reaching the Andes in most cases. And there you have this expression. We probably would not have, we still would have an Amazon, but not probably as diverse and biodiverse and as rich as this has been for the last few thousand years. Here you can see the moisture coming from the trees itself, from the vast forest. I took this picture from a platform in the Tipitini area, and you can actually see, oh, this is not fog per se. This is the water material from photosynthesis by the plants and plant leaves being released into the atmosphere. And that, of course, is important. But what's important is that this wouldn't happen without the flow of iron and sulfur in this important compound, ferredoxin, which is so central in the electron transport chain of photosynthesis, as you know, in plants and in trees generally. And we see that expression here, right? I mean, these are all highly photosynthetically efficient and again, releasing huge amounts of water. But this, again, a lot of this is because of some of the iron flow coming from the little Sahara region, some of the sulfur flow as well. And this ferredoxin really is a contributor to transpiration, movement of the water upward. It condenses and forms clouds and low pressure systems, much of which the water then falls back down onto the Amazon and keeps it going but it also forms low pressure systems that move around the planet and can actually, in any part of the world, particularly in the northern hemisphere, it's conceivable that you could take a drink of water that that had its direct and indirect origins, not just in the Amazon, but in this story. Okay, we have a reservoir system in Massachusetts here, Quabbin Reservoir, which is fantastic. It's surrounded by no industry, so the water is particularly high quality and no toxins. And these reservoirs certainly get rainfall, and some of that rainfall certainly has come from low pressure systems that partially had their origins in tropical rainforest environments. So there's real connections here beyond what we can imagine. Those connections, ancient and recent microbial life, are really the basis of the Chad story. Once they dry out and go through their cycles, they are an important feed to the Amazon tropical rainforest, as well as to other areas in the Atlantic and other areas of the world, really. And they can build low pressure systems or contribute to it, which keeps the Amazon going and nice and wet. But it also at times can feed back to Lake Chad at certain times and climate periods where there's substantial rains in that southern area of Chad or south central area of Chad, and can resurrect the lake to some degree, enough for more diatoms to grow. Yeah, you got it. So a lot of the biodiversity of the Amazon is, again, in terms of another wow, is due to this element flow, this building of a platform that we call the Amazon rainforest. And it comes from another platform, which is essentially the collection of sponge cafe, particularly phosphorus, iron, and other elements in the Baudelaire region. So again, and it stores it for long periods of time. It releases it through wind and serves as an important nutrient source, etc. And look at these are all pictures I took there. I think. Let's see, are there any that I stole from anybody? No. Uh, and this is lovely one. Of course, fungi is so beautiful. Most of them are really. And this, of course, is not a plant, but it certainly is a great mimicry one, isn't it? It's a caterpillar. That's mimicry is the name of the game, right? And the rainforest, those of you who've been there know about it. It's so dominates mimicry and camouflage. It's really the home of the rare, right? The most biodiverse and prolific areas for life are also the ones with the most rare organisms, because each organism has to really form its own niche in order to keep rolling forward. This is a picture taken, and you can see some of the transpiration there in the morning. It has this bizarre light from a tower that we took. And over here on the left is a massive um, moth feeding on some fungi. And this is one of the most important organisms of the planet. It's a scat or feces roller and depositor. This is the dung beetle. And boy, world would be different if we didn't have organisms taking this and making nutrients go into the upper portions of the Amazon. All of the scats, the droppings of animals, disappear. They're taken by the dung beetle that deposits its eggs in there. And of course, it also becomes a great nutrient source, etc. This is a story in and of itself, right? So the Amazon, its immense global importance here. We won't go through all of these. But one, again, its importance is the element nutrient flow on a global level, extending right back to some of the origins of it, which is in North Africa. 20% estimated the world's oxygen, the rest is from algae. And of course, there's some evidence that they also tend to hold in their viruses, that the viruses really get extended to broader communities once humans are there and extract other organisms that might carry the viruses. So that extraction can be problematic. Element flow capture. And of course, a big one here is a major carbon sink. Where would we be today? What temperatures would we be at today if there was no Amazon? Amazon is is pretty much close to the size of the contiguous United States. That is, drop off Alaska and Hawaii. And the 48 states of America are pretty much the same as the size of the Amazon, albeit the Amazon, just like California, is severely threatened by climate change connected rain, fires, and very little rain. So we have major threats here. And of course, this is a major carbon sink. And that's why I always argue that trees are easily our best friends. You could search forever, and I'm not sure you'd find a better friend than trees to our very survival and the survival of all our creatures around the planet. So all of these organisms, algae are major wow makers. Okay, we've seen here the one, the dinoflagellate in the lower right, the diatom here, the coccoliths. And as I wind up my chatter here in the next few minutes, just pointing out that who would have thought that algae would have such a major impact, but they do. I like them from the Melibacea and other red algae here to the coccoliths in the upper left to the diatoms, as we saw there in northern parts of Africa. And we see here dinoflagellates, which become encysted, don't look like this when they're part of the coral, but we wouldn't have coral reefs without this alga. So sometimes algae don't get the attention they should, and they really are, really along with bacteria, as you know, running the show. And we're latecomers. Why are we such a, and one thing to note about them is they're also symbiotic. They're not, mutation is not their central way of coming to be. They come to be through symbiotic processes. We now have good evidence that all of the eukaryotic algal lineages, not just the chlorophytes and the rhodophytes, resulted from this primary symbiosis of a cyanobacterium entering into a mitochondria-containing host organism that's somewhat amoeboid, perhaps, and eventually was tolerated and evolved to these kinds of differentiated systems with an offshoot into plants here from the green algae. You know all this. But some things that didn't become clearer until the last 20 years is that all of these other organisms became symbiotic by a red algae of some type being taken in by another host, non-photosynthetic organism, protist, and becoming another photosynthesizing alga, a cryptophyte. There's another one here, taking a red alga being taken in. We call this secondary symbiosis, being swallowed up and 99.9% of the time eaten, gone, but in a small percentage of time tolerated. And then you have mutational expressions such that it's retained along with all of these genes, which then get sorted out and become one dynamic organism that was once this primary and secondary symbiosis, now into a unified whole, this holobiont, as we call now, right? This collection of different genes that then become kelps, diatoms, chrysophytes, haptophytes, etc. This is an amazing story in itself. To me, it's most amazing of all, in a sense, because we always think of evolution as proceeding in this gradual way and through just simply mutational recombinational events. Yeah, of course, it's important, it's central, but you can't leave out the fact that the origin of this is through an attempt at digestion, is an attempt at taking in something. And then that taking in becomes permanent in some small lineages over time and then evolves into these massively important organisms that we've been just hearing about and seeing. So that's a wow in and of itself. And this is the amount of time that we've been on the planet. Humility is very important before I close off. I always have to give my little humility thing. I know we're at the hour point, so if you can't stick around a minute, if not, you can see the tape later. But here is, we're just really at the tip here. As we've said, many of you know this from my talks, we're really just, we're the manicure. We're just the edge of the fingernail. We just go back, roughly 200,000 years in terms of someone that looks like a primate, something like us, a primate that looks like us. But most of Earth time, of course, as you know, is not only eukaryotic, but prokaryotic, dominated by microbial life. And very successful. All the main things that we depend upon, photosynthesis, respiration, motility, whatever, they're all invented and successful hundreds of millions of years before us. So we're just a latecomer, and I'm not sure, but in my opinion, and this is where people don't like me very much, we really are not becoming part of the biosphere. We're still not really part of the biosphere, at least not modern humans. Perhaps indigenous people who live close to the land and didn't have inventions and creations of material things. We have to remember that these material things that build houses, all these white areas where the rainforest was on the left, this is the same area now being housed by many people. People have to live somewhere. But on the other hand, taking so much land and expanding becomes suicidal in the long run, doesn't it? It becomes a danger to all life. We're in the sixth extinction now, but to humans, because we're extracting, we're taking away the systems that run the planet, and therefore we're not part of the biosphere. None of the other creatures on the earth create these constructs, okay? None of them. So we're, to me, still outsiders, and we'd have to change drastically, and maybe that's what we have to do, to become really part of the biosphere rather than something that is working to shut it down. And if you're still not clear, there are hundreds of pictures. This is what's happening to the boreal forest in Canada. And this is the same area. This is the same picture 3 years later. This is not recoverable, at least thousands of years. And so this is for oil extraction again, fossil fuels, which is crazy to keep depending upon, really. I mean, it's just destructive to our future, ultimately. And this is, we sometimes don't think of it, but this is one of the last pictures I'll show you. This is a picture in Vietnam. This is before bombing. This is after bombing. We don't think of warfare as being destructive to the environment in a major way, or at least as a story. And of course, we see here the rainforest being destroyed in the Vietnam War. But we could take pictures from all kinds of war scenes. And we also know that we have 13,000 nuclear weapons. So we can see right away that this is not part of the biosphere. In the millions and millions of years, there's no systems developed that way. Sure, you have volcanic action, destruction, meteor hitting the planet, etc. But you don't have this short-term, consistent damage, particularly to a species that has quickly developed all of these things. So, and bringing down so many other organisms. We really don't need to be the meteor. The meteor needed to be, so to speak. It was just part of the cosmic expression back 65 million years ago at the KT boundary, as we say. Okay. So this is the last thing I'll show you. This is the calling home. If people want this, a copy of this, I can send to you, but it's also great to just see it. You have to go onto a real laptop computer because a laptop computer would handle it better, whereas a cell phone doesn't so much. And when you go onto the site, it has a lot of great things you can look at here, and lots of good pictures and so on, and good stories to see. So I urge you to access this site. If you don't have the listing itself, you can just see it on the recording, what have you. But it's part of the Global Ecology Education Initiative. We put something like this out each year. This is Nyamonte. She is a great leader in the Amazon and has managed to fight off Chevron and to some degree, and others with the Warani peoples and help of lawyers, and trying to limit and get rid of the constant killing off in the Amazon. A lot of it due to extraction. Taking out, taking away, taking out for oil and other minerals. So those are the wows for today. Thank you for sticking around so long. Sorry I went so long. And my apologies. Hopefully some of it was worth staying in for. Questions, comments? I'll finally be quiet. God.
Yeah. Thank you very much, Professor Zook, for a very interesting talk with so many examples and so many beautiful pictures of you. It was really great and very interesting. Does anybody would like to ask something, to comment on something? Don't be shy.
Oh yeah, no, you can't.
Yes, this is the only opportunity to ask. Maybe not the only, because you can contact, of course, Professor Zook via email, for example, but there is a chance to discuss directly.
Right. Who are some of my friends out there? Let's see, is Professor Turner out there? Well, maybe she wasn't.
That's not really.
She's
not. She's not.
Monica, you there? Of course, you have a lot of Monicas, but you know, who else is out there that I might know?
No, Monica is also not.
Okay. Well, if there are any questions that people have afterwards, they can, again, like you say, always email, and of course, through the recording, people can get in touch.
For me, the most important thing, the key message, I would say, from your lecture is that everything is connected. Yeah.
Yeah.
What you are doing here, your daily activity could have an impact on people, on environment far away from you. Yeah.
Absolutely. Yeah, and that's a great way of putting it. The unity of nature. In a sense, that's almost the definition of global ecology. Yeah. It's the connections over great distances. And yeah, I was making the point at the end. I didn't have to, but you know me, I have to say my story. But we need to be more a part of the connection rather than a problem in the connection, you know. Yeah. But yeah, you hit the nail right on the head, as we say, in that it is a lot, these stories, the unity of nature, how things are connected over time. They change, but the influence is profound. Something that happens in a faraway area can affect us right in our own community, and vice versa, the other way around. But I think that the big story here too is that when we think about it, it's mostly these 9 elements that are flowing too. That's the big connector. There are lots of other elements, but they're really minor players in the play, in the story. The big players are just the 9 of them. And who would have thought of that? I mean, that you could have such diversity coming from just those small number. I mean, if I didn't know anything and came from another planet or just didn't know anything about science, I'd say, wow, there must be thousands of different combinations and elements going on. And then you look at the periodic table, it's not many, yeah.
Great.
Excuse me, maybe it's not a question, but I would like to say that I really appreciate the way that you showed those elements to me today, because usually I'm looking for like more biochemical point of view, so from very, very close, and today I saw it from like wider and different perspectives, so thank you. It was really nice.
Well, that's great. Yeah, well, I'm glad. Yeah, it works. And I have a lot of people and students that I have in my global ecology course or over the years who I'll see them on the street or say something and say, oh, I still remember the Sponge Cafe.
Yeah.
And I say, yeah, great. It's not cappuccino and lattes. It's a different cafe.
Okay. Anybody else who would like to say something? Okay, so
we can close out here.
Sorry?
we can close out here if you'd like. We can stop.
I think so, that if you would like to contact, so you have email, yeah, of Professor Zook at the screen still, yeah, so you can contact him, of course. So, Professor Zook, thank you very much for your very interesting talk. Thank you all for joining us today, and hope we see all pretty soon directly, not via electronic devices. And I wish you all good luck, and see you soon.
Yes,
Thank you very much.
and I thank you very much. You're terrific. I thank you so much, Annette, and everyone for joining in. And I do believe that, you know, we've lost maybe a few people here because I went so long, over an hour. People do have another life, and I'm sure there's other things to do. So, but I thank everyone for coming in, and hopefully people will, who missed the last part of it, will see it maybe on the recording as well.
Yeah, so it's recorded, so it will be on our channel, and I will distribute it. I will also put it on YouTube channel of the Instytutu Botaniki, so I'll try to distribute it as much as possible for those who were not able to attend today, or for those who need to quick it earlier. So I hope that more people. We had 27 attendance today, so not
Great.
so bad. 27, yeah. I will send you a list of people who attended.
Oh,
meeting.
great! That's wonderful.
Yeah,
Well,
so it's not bad. Thank you very much once again, and see you.
okay, thank you again, and I'll be in touch. I'll talk to you soon on the email, right?
We will be in touch. Yeah, of course, we will be in touch. Please think over this invitation for
Yes.
this. Yeah,
Yeah, definitely. I'll write about that. I'll probably have a few questions, and we'll move that. Yeah, that'll be great. Okay, great. Thanks again.
So thank you for great lecture, and it's a bit intimidating this way on Microsoft Teams to ask questions, honestly. So I hope one day we will be lucky enough to attend your lecture or like lives.
Okay.
I'm persuading him. Yeah, I'm persuading him to come here and to give us speech, which will be much longer. So I mean the whole course, which will be devoted global ecology. So I hope
Yes, that would be great.
It will be possible next term, I think. Yeah.
Yeah, and honestly,
Or next year. Yeah.
Yes, and honestly, it's great to just be back in Krakow. It's one of my favorite places in the world. It really is. There's no question, and the people there that are just terrific. So I look forward to seeing everybody again.
We also. So you are kindly invited, of course, as always.
Yeah.
Okay.
Take care.
So, once again, thank you very much, all of you, and goodbye.
Bye. Thank you.
Goodbye. Thank you.
Thank you very
much. Thank you very much.
Bye.
Bye. Bye.
Thank you very much. Goodbye.
Bye-bye.
Thank you. Good night. Goodbye. Good night. Goodbye.
Thank you very much, Professor.